Okay, good morning. So I want to talk about a topic that's related to chi-boundedness. So here's the plan. So I want to spend a minute on perfect graphs, 2 minutes on divisibility, perfect divisibility, and chi-boundedness, 3 minutes on 3 results that we have. Okay, this is joint work with Maria Chudnowski, and 4 minutes on questions and problems. So I've been given 10 minutes, which is a triangular number, so I should be okay. Okay, so all of our graphs are finite and simple, and the notion of containment that we are interested in is induced subgraphs. So you take a graph and all you can do is just to delete vertices. That's all you can do. So it's a very strong notion of containment, and here is a classic definition, probably the single most influential definition in graph theory in terms of it's not an easy definition to make in the sense, and it crops up in so many places like polyhedral combinatorics and so many other things. So in my mind, I think of it like Whitney's definition of a matroid. So a graph is perfect if two invariants are the same for all induced subgraphs of the graph. And what are the two invariants? The chromatic number and the clique number. So the clique number is the size of a largest clique, and a clique is a set of vertices, set of pairwise adjacent vertices. Okay, Bert defined this in 60s, and it has since then become an area of graph theory in itself. And he had two nice conjectures which were proved. And the main point is that if a graph is perfect, its complement is also perfect, and there is a forbidden induced subgraph characterization of perfect graphs that is exactly odd cycles starting at phi and their complements. So that's kind of the starting point. So once you have perfect graphs, there are a couple of things you can do. So you can take that as an axiom and then work only with perfect graphs. And you can kind of zoom in, and there are so many classes inside that come from other objects like partially ordered sets, and there are so many classes like chordal graphs and so on, and that has a very algorithmic flavor. So when you go inside perfect graphs, you have more and more structure, and you can do a lot of things. But there is another way to go, which was envisioned by Gerards, which is the notion of chi-boundedness. And before we get to that, the thing that we are interested in is called perfect divisibility, which is a definition due to Chin Huang. And here is the definition. You have a graph, and for every induced subgraph, you can partition the vertex set into two pieces such that one piece is perfect. So you have your vertex set, you can partition into two pieces. So one piece is perfect, induces a perfect graph, and the other piece has a smaller clique number. And you want this for every induced subgraph, so you can repeat this over and over again. Okay, so that's called a perfect divisible graph. And here is a definition due to Huang and McDiarmid. So a two divisible, if you do the same thing, except that you don't care about perfect graphs anymore, so you divide into both pieces smaller clique number. Both pieces have smaller clique number. Again, the crucial thing is for all induced subgraphs, so that you can keep doing this. Okay, easy observations. If you have a perfect divisible graph, you easily get a bound for the chromatic number in terms of the clique number. You get a quadratic bound. And if you have a two divisible graph, you can keep doing that, and you get a bound which is 2 to the omega. Okay, so this leads us to the notion of chi-boundedness. Gerards' notion of chi-boundedness is if you have a specific function such that the chromatic number is f of the clique number, then that's a chi-bounding function for a class. And a famous early result is that the whole class of graphs is not chi-bounded. There are triangle-free graphs which have arbitrary large chromatic number, and Erdős generalized that. You can have large girth and large chromatic number, arbitrary large girth and chromatic number, and so on. So here are three very basic questions. If you have a class, is it chi-bounded? If so, is there a polynomial chi-bounding function? And you can be even more greedy and ask for a linear chi-bounding function. And why do we care? Well, for approximation algorithms and things like that, but also for a famous conjecture called the Erdős-Heinel conjecture, which is, can you find a big stable set or clique in your graph? Big means n to the epsilon, where you have to fix the epsilon for a particular class. And the conjecture is that it's every graph class has the Erdős-Heinel property, except the whole the class of all graphs. That's not true. But as long as you go to any hereditary class that doesn't contain all graphs, you have the Erdős-Heinel property. And when you have a polynomial chi-bounding function, if the polynomial has degree d, then you can easily get your epsilon to be d plus 1. So you easily get the Erdős-Heinel property out of a polynomial chi-bounding function, but not otherwise. Okay, so here is a fancy conjecture which says that the bullets 1 and 2 are the same. If you have a chi-bounding function, you always have a polynomial chi-bounding function. So, okay, so let me get to the results. So our first result is that if you don't have these two graphs, so this is P phi, path of length of path on 5 vertices, and this is C phi. If you don't have these two as induced subgraphs, then you are two divisible. And the other thing is, if you don't have a bull, which is this graph, and if you don't contain odd holes, you are perfectly divisible. And the third one is, if you don't have a P phi and this, you are perfectly divisible. So I think if I have, so the last two depend on structure theory of bull-free graphs developed by Chudnovsky and Chudnovsky-Safra. But the first one is self-contained, so I think I'll just dwell on that for a minute. So how does the proof go? So you have a graph that doesn't contain P phi and C phi, and you have to show that you can partition into two pieces such that each piece has smaller clique number. So you start with a vertex, you take its neighbors, and there are other guys. The other guys fall into components. So you have a vertex, you take its neighbors, and when you delete this, it falls into components. So call it C1, C2, CT. So, okay, we may assume G is connected. So that's the slide. I'm just calling it M, okay, and it falls into components. Okay, so if it happens that, okay, a vertex is said to be complete to a set of vertices if that vertex is adjacent to everybody in that set. That's the word complete. If it happens that each of these is complete to somebody here, then you get your two partition by just, this is your two partition. So this piece, well, I mean, you can put V here. A simple observation is the neighborhood set of a vertex has smaller clique number. In a graph, if you take a vertex and take its neighborhood set, it cannot have a biggest clique. So you get that easily. So we may assume that no vertex here is complete to this. So we arrange that in such a way. Actually, you can show that all of the others, for everybody else, there must be a vertex that's complete to it. Because if not, you kind of go this way and you get your P phi. You have to be a little bit careful, but I think it can be easily shown. Okay? Okay, here's the main point. So from all these vertices, choose a vertex, call it N, which is adjacent to somebody in C1 that has the maximum number of neighbors in M. Okay. So, and what happens is that, and we get the partition. This is the partition. You take the neighbors of N. I mean, N could have neighbors here. And you check that that partition works. That X2 doesn't contain a clique of size omega. I mean, in a second, so what would happen is that you get something like 1, 2, 3. You cannot have a configuration like this because no matter what happens here, you either get a P phi or a C phi. Okay, so that's kind of the proof. The other part, as I mentioned, involves structure theory of Chudnovsky and Safra. So let me not dwell on that. Okay, conclusion. It is NP-complete to determine whether a graph is perfectly divisible, but the complexity of two divisible graphs is not known. So that's an open problem. But there is a result of Seymour-Chudnowsky on K4 free, odd hole free graphs that could be useful to prove this. Are P5, C5 free graphs perfectly divisible? Can this proof be adapted to show that it's actually, because this is the first open case for Erdős-Heine, P5, C5 free. So a polynomial bound would be nice. Okay, another conjecture is that a forbidden induced subgraph characterization of two divisible graphs is exactly that of odd hole free graphs. Okay.